Welcome to Medha here. Without wasting time, let us start today's session with this question. The question says, if we have 0.32 gram of metal that on treatment with acid give 112 ml of hydrogen at NTP, we have to calculate the equivalent weight of the metal. To solve this problem, you have to know one concept, that is 1 mole electron that is equal to 1 equivalent of electron. Now if you consider this reaction, H plus an electron, it will give you half mole of hydrogen gas. Now see, we have 1 mole electron here and half mole hydrogen gas here. But remember, there is one important concept, that is in case of any chemical reactions, reactants or products react or formed in equivalent amounts. Now if 1 mole electron is 1 equivalent, so this 1 mole electron is 1 equivalent, that means half mole hydrogen will also be 1 equivalent, because both react in equivalent amount, same equivalent amount. Now we have this relation, half mole hydrogen is equal to 1 equivalent. So 1 mole hydrogen gas, it will be 2 equivalent of hydrogen. Now in this question we have 112 ml of hydrogen at NTP. Now we have to calculate the moles of hydrogen. So moles of hydrogen in this case, it is 112 divided by 22,400. So that is the mole of hydrogens. Now if we calculate the equivalent of hydrogen gas, that will be 112 into 2 divided by 22,400, because see here, half mole is 1 equivalent, so that means we have this mole of hydrogen, so we have to multiply that one by 2. Now the metal, it reacts with proton, it gives hydrogen gas, right? Similarly we are getting electron from here. Now check, we have 112 into 2 divided by 22,400 equivalent of hydrogen, so that will, here it will be same, so 112 into 2 divided by 22,400 equivalent, so that is the exact same amount. So that mass equivalent is equal to 0.32 gram. So 1 equivalent of metal, is equal to 0.32 into 22,400 divided by 112 into 2. If we calculate, that will be cancelled out, that is 32 gram. So the answer in this case will be 32 gram. So equivalent weight of the metal will be 32 gram. So again, if we summarize this problem, so the concept that we have to know, that is half mole hydrogen is 1 equivalent. So first we have to calculate the mole of hydrogens, and then we have to calculate equivalent of hydrogens. That mass equivalent is exactly same equivalent of metal will react, and from there we will calculate the equivalent weight. But if we solve this problem in a short, that will be like this. So equivalent weight of metal, that will be, say, mass of metal into (11,200) divided by volume of hydrogen at NTP. Now see, this formula you may have seen in different websites, but how this formula came, see, this 2, if we multiply that one by 2, that will be 11,200, and below you have to put the value of hydrogen gas. So by simply using this equation also you can solve this problem. Okay, I hope it is very clear to you. Okay, let's see problem number 2. Identify the site where protonation is favorable. So this is, I think, important question. Say in this question you have two sites where protonation can occur. One is oxygen, another is nitrogen. But here the lone pair of nitrogen is taking part in conjugation, and that's why the lone pair will not be available for protonation. That's why the most basic site here where the protonation will occur, that is oxygen, where negative charge is actually forming. That's why the answer will be A in this case. So that is the answer. Okay. Next, see problem number 3. The geometrical isomerism is shown by, as you can see in this problem, the normal that rule you have learned from here, you cannot say which one will show geometrical isomerism. But if you see the resonating structure of this compound, resonating structure, then you will see, so here we have NHMe. Now if we do resonance, then the resonating structure that we are getting here, this compound, you can see two different atoms. There is a restricted double bond. First you have to check whether restricted double bond is present or not. So here we have a restricted double bond, that's C double bond N, and each atom of the double bond have two different groups individually. Here hydrogen, here CH3, here CH2 negative, and here H. So two different groups individually we have. That means it will be the answer in this case 1, that will show geometrical isomerism. Okay. Next, see problem number 4. To understand this problem, you have to know the mechanism of Hofmann-bromamide degradation reaction. So let me explain that one very quickly. So if you have amide, that amide first react with base, we are writing the mechanism of Hofmann-bromamide degradation. So here we will get NH negative. So here one hydrogen from the nitrogen atom, it will be removed. Now this negative charge is, this anion is resonance stabilized, and that one react with bromine. So if it react with bromine, this negative will attack and you get bromamide, C double bonded O, NH and Br, that is bromamide. Now this bromamide as a hydrogen, that is acidic hydrogen. So this one acidic hydrogen. Now this acidic hydrogen can again be removed by this hydroxide ion, and you will get a negative charge on this carbon atom. RC double bonded O, N negative and Br. Now the important rearrangement will occur here. That rearrangement is, nitrogen will form a double bond. This R group will migrate from the carbonyl carbon to the nitrogen, and then bromine will remove. So this is the mechanism of the reaction, rearrangement step, and then you will get isocyanate. After hydrolysis of this isocyanate, you will get the desired amine. That is the mechanism. So remember, you have to form this bromamide where you should have acidic hydrogen. You should have acidic hydrogen. So that's why substituted amide will not react. Substituted amide will not react. Where, see, in option number 4, you don't have any acidic hydrogen. The first case, the reaction will not occur. But other options you can see, in this we have acidic hydrogen, 2 hydrogens, here also 2 hydrogens. This one is already the intermediate, this intermediate, so it will react. But the fourth one, it does not contain any acidic hydrogen. So remember, substituted amide will not react in Hofmann bromamide degradation. So that's why the answer in this case is 4. I hope it is clear. If you have any doubts of this rearrangement, you can comment below. Okay, so I will definitely make another video to explain that one more. The last problem we have, in Cannizzaro reaction, the intermediate that will be best hydride donor. So here we have negative charges. So in this question, you have to think about that one. If any molecule is a hydride donor, that means electron density of that molecule should be higher. Now see, among these options, option C has the highest electron density. You can see the lone pair of this methoxy group, it can be donated to the benzene ring, along with these electrons can be donated, and this hydride will be removed. So more electron density, it will be easier to remove hydride ion. That's why best hydride donor in this case will be option C. So thank you very much for watching this video. If you want more videos like this, please hit the subscribe button and also the bell icon. One good news for you, we are going to open a new branch at College Street, Kolkata. So if you are interested to join our classes, please WhatsApp to this number and follow us. Thank you.